that table?
I'll set it up soon. And then send an email to everyone.
Okay. So basically what we want is for you to have access to all the lectures ahead of time. And we set up a Dropbox folder where basically all the lectures will be there. And for now, I guess we'll survive with these first couple of lectures here. Like this. So this is a very basic introduction to light scattering, microscopy, even light propagation in vacuum. Some of you will roll their eyes, and I'm going to show you a plane wave, for example. But the idea is really just to warm up, okay? So one thing that I'd like to ask is how many of you have used Fourier transform? Okay? So, most of you, but there are some who didn't. So I personally think that probably is the most important mathematical tool that you could use in optics. So I encourage you to start reading about it if you haven't used it yet. And basically, I'm going to use it very immediately in this lecture. So this is, I'm going to talk about two chapters basically of a book that is on quantitative phase imaging. Don't worry about that. But I'm going to use two chapters that are introductory to just light propagation and scattering, chapter 2, and then chapter 5 is on microscopy. We're going to talk about resolution, things like this. So really 2 hours of just kind of warming up, okay? So, basically, I'm sure you know how the Helmholtz equation looks like, okay? So this is it. What is Helmholtz equation? Well, it's the wave equation that is basically from r, coordinate r and time, we transform it into coordinate r and frequency. So Helmholtz equation is the wave equation in space and frequency. So what do we do then? Why? When are we going to the frequency domain versus just space and time domain? For those who have used Fourier transform. The idea is that when you look at the signal in time, such as a light pulse, for example, it helps you to decompose that signal into many different sinusoids of different frequencies, different amplitudes, and different phases. So any signal, it turns out, can be decomposed into sinusoids like this, of various amplitudes, frequencies, or periods, and phases. The Fourier transform of this signal, so this will be a temporal signal, that is made up of these different sinusoids. The Fourier transform tells you exactly how much of this frequency I need to put in, what's the amplitude of it, and what is the phase, how much do I need to shift that sinusoid in time. And for any linear process, the best way to solve a linear problem is in the frequency domain. Meaning, what it means is that I'm solving frequency by frequency, and then I'm adding up the results. This is a fundamental principle of superposition in physics, in all physics. And that's where the Fourier transform comes in. And basically the Helmholtz equation says that once I put it in the omega domain, it means that I'm solving at each frequency omega. And if I find a solution as a function of omega, and then if I want to go back to time domain, I take the Fourier transform at the end, which is to say that I'm solving for each frequency and I'm adding up the results. Okay, so this is the very basic reason why I would like to solve things in the frequency domain, just because whenever the interaction is linear. Okay, so what do we have? Well, we have a Laplacian, right? We have the field itself, U, and then we have K naught. This is a property. Okay, thanks for setting up the Dropbox. K naught is omega over C, right? And what happens when we propagate light in a medium that is not vacuumed? How does K naught change? If I'm in a refractive medium of refractive index n, what's K naught going to be? K naught becomes N times omega over C. So you see, K naught has the material properties inside. For a frequency omega, if I am in a medium of refractive index n, K naught is set. Because C is just a constant, right? The speed of light in vacuum. So what do you think the meaning of this K naught is? What's the unit, first of all? The unit is radians per meter, or more realistically, per micron. But to understand the meaning of K naught, what it tells you, we can do a very simple thing from this equation, and then we are going to move on with our lives. I would like to take the Fourier transform of this in space. How many of you know what the Fourier transform of a Laplacian operator is? It's a second order derivative in space. Do you know what that will give you in the frequency domain?
Omega squared.
Omega squared, if it was a derivative in time, so if I have d at dt, in the frequency domain, this will translate into I omega. If I do d2 at dt2, this operator is going to become I omega twice. It's going to give you minus omega squared. Good. But now, so imagine if I take the derivative of u, this is going to be u of t. This is going to be I of omega times u of omega. Somebody needs to turn this off. But now, similarly in the spatial domain, if I have the del operator applied to u of r, it turns out that this actually transforms into come on. Okay. This transforms into I k vector. Right? So this is a gradient, it's a vector. In the frequency domain it becomes I k times u of the k. If I do this twice, it will become I k vector times I k vector. It will become minus k times k, which is k squared. So what's the meaning of k? This is a spatial frequency. In the same way, omega gives you how many cycles per unit time you have, how many radians per unit time. Higher frequencies means that the oscillation is faster in time. K gives you the same thing in terms of oscillations in space. Higher k means, if you look at the field in the spatial domain, you have the frequency much higher. If you, for example, the phase change will change much faster per unit space. So now we're able to write this in the frequency domain. So you see, if I take the Fourier transform of this whole thing, let me write it down here. What do I get? The Laplacian gives you minus k squared, and k now is the magnitude of the vector k. This is just the length of the vector, right? K naught squared stays the same. Becomes u of k and omega equals whatever the source term is, s of k, Fourier transform. I can put tilde to indicate Fourier transform. Yeah?
You're off the board a little bit there.
I am? How about now? Quickly. So why is this interesting? Let's imagine I have no source. I have a field propagating in vacuum. Somewhere in the region of space there are no sources. So if I do this, if I make it equal to 0, the non-trivial solution means that k squared equals k naught squared. And what is this equation called? It's called a dispersion relation. Dispersion relation. It tells you that if you have a certain, if you have a certain frequency, so remember this is omega squared over c squared. If I have frequency omega propagating in free space, the amount of change per unit space, the k, the spatial frequency k, is fixed. It's fixed at omega over c. So k naught is a property of the material, right? It has c, which is a universal constant. It has omega, which is a frequency. If you have n, it goes in there. So that's a material constant. And you have k, which is the spatial frequency of your field. What the dispersion relation tells you, when there are no sources, they are equal. Okay? So this little equation is perfectly and entirely equivalent to having the full wave equation. So the dispersion relation is not an additional equation to the wave equation. It is the wave equation in the space, in the frequency domain. Yeah.
So in the context of basically optical waves, is there any specific assumption that for the Helmholtz equation?
To hold?
Yes.
So the only assumption for the Helmholtz equation is that the field is scalar. So notice that usually we have an electric field that is a vector, right? So a vector that has three components, Ex, Ey, and so on, Ez. I made a mess. So whenever we have field distributions that are fairly smooth over distances of the order of wavelengths, okay? So for visible light, if you don't have very tight, very small structures of the field, very tight focuses, for example, right? Very small particles or nanostructures, then it's okay to use basically just one component of the electric field, let's say Ex. And then you replace the vector field with a scalar field, U. So that is the only assumption. But the Helmholtz equation is basically, for scalar fields, is full, no approximations involved. Taking the Fourier transform of it also doesn't lose any information, meaning that the dispersion relation actually has full information, in this case for vacuum propagation. And it equalizes two different things. I want you to have this very distinct in your head, that k as a vector is a spatial frequency. It's the wave vector associated with your wave. K naught is a material. It has omega in it, it has n, and it has c. But the wave equation tells you that they have to match. You cannot have random spatial frequencies, right? They are matched by the properties of the medium and these universal constants. And to make a connection, I know all of you know what dispersion is, and that's something to do with the refractive index being a function of omega, right? So the reason we call this a dispersion relation is because k squared for a medium that has a refractive index n of omega, you see it's going to be n of omega squared over c squared. Right? So if you have a crystal or something, or a piece of glass that has dispersion at different frequencies, you have different refractive indices. The spatial frequency k, the wave vector k, the length of that is set by the property of the material, how big the refractive index is for this particular wave frequency omega. And c is just a constant. Okay? So that's the fundamental result of the wave equation. It sets, it matches these two quantities. Is not an additional, I know all of you have heard of k equals omega over c. So probably all of you have used that in the past. But I want you to think now of it as a result, as being the actual wave equation in the frequency domain. Okay. I want to review two things. Imagine you have a source that is actually an infinite wall on the x-axis that emits light. Okay, so that means my wave equation becomes one-dimensional, so I have a source that is a delta function in x. So what that means is I have, I'm going to delete this, I assume there's some of it. So the situation is like this. This is the wall along x, infinitely thin. That means your source is a delta function in the x domain. So very thin in x, infinite in y and z. And I want to know what's the solution of this. What's the field coming out of this plane, planar source, like this, right? How do I solve this? As I mentioned earlier, the best way to solve any linear problem is in the frequency domain. So we use what we did earlier. Fourier transform of this g, I call it g because it's the Green's function, any solution to a delta function, right? It gives you the Green's function for that problem. So essentially what we are solving here is a one-dimensional propagation from a planar source. This is the Fourier transform of that equation. So you notice kx, this is my k that has only one component because everything else is constant in y and z. So the wave only kind of oscillates in x. Fourier transform of the delta function is 1, even though you don't know Fourier transform, some of you maybe.
Direct.
Remember this?
Is that direct?
Direct delta function, yes. If you have a function that is narrow in one domain, it becomes fat in the other domain. So narrow in the spatial domain becomes fat in the frequency domain, and vice versa. So for example, to generate a short pulse, laser pulse, you need a fat gain in the frequency domain, right? Broad spectrum. In time domain, in microscopy, if you want to focus light to a very small point in confocal to obtain high resolution, you need what? High angle coverage, high numerical aperture. Okay, it's the same, that's the result of the same probability of Fourier transform. Delta function is the ultimate skinny function, right? It's the skinniest function you can get. It's actually the width is 0, which means that in the frequency domain is the ultimate fat function, which is a constant. So Fourier transform of delta function is 1. So basically, you can write, you just solve this equation. So you see in the frequency domain, this equation becomes a fifth grade equation, right? So I can solve g from here. It's 1 over k naught squared minus k squared. This is the full solution, except that it's in the frequency domain. It's in the kx domain. So you notice you go from a differential equation that looks like this. In the Fourier domain becomes an equation of 5th grade equation, right? Algebraic equation. The solution is this. The Green's function in the kx, in the frequency domain kx and omega looks like this. And now, there is a trick that we can employ. We break this denominator into two terms, k naught plus kx, k naught minus kx. And what's the meaning of that? So one will be kx going this way, so being positive. The other one is kx being negative. What does that tell us? That there, from my infinitely thin wall that emits light, imagine you sprinkle the plane with quantum dots, but they're also coherent. Because my delta function assumes they're emitting at the same time, right? So I have that plane that emits light. Essentially, I have waves going to the right and waves going to the left. That's the meaning of those two terms. And what is the Fourier transform for 1 over kx? It turns out that it's the signum of x. The signum function, right? So it's a plus 1 for positive function and minus 1 for negative function. That looks like this. Right? So altogether, when you bring the solution from kx to the x domain, you get these two exponents. Oh, there's one property that I want you to kind of remember, and that is the Fourier transform of a shifted function, let's say kx minus k naught, will be taking the Fourier transform of a shifted function is the Fourier transform of the unshifted function f of x multiplied with complex exponential that has k naught in the exponent. That's called the shift theorem in Fourier transform. So, what does this exponent remind you of? e to the I k naught x. What does Huh? Well, let's look at it. So first of all, we got two waves, right? We have a constant here that has the k naught in it, so omega over c. And then I have a simple exponential. One is positive, one is negative. So I have a wave that goes this way, another wave that goes backwards from my planar source. If you combine the two, you get a real thing. But normally we'd like to use the complex version of it. Well, let me take a second and tell you what the complex analytic signal is. How many of you have heard of a complex analytic signal? Okay, not that many. So the thing is, in the lab we deal with optical fields that are real. Okay. So what we measure, they are very real quantities. But it turns out that it saves us a lot of trouble if we associate to that real signal something that is complex. We call it complex analytic signal, which simply, we construct it this way. So the simple example is the cosine of kx is a real function. But I construct e to the I kx, whose real part gives me the cosine, the original signal. And then I have an imaginary part that is actually related to the, so sine and cosine, they are related, right, through a derivative or through a Hilbert transform. So, but it helps me to get rid of trigonometry. So when I don't deal so much with cosines and sines, I deal with exponentials, which is much nicer. So that's basically the reason we are working with complex analytic signals rather than the real signals themselves. So that's the reason that in general, the solution that we work with to this one-dimensional problem, it looks like this in the complex form. And this is what we call a plane wave. Why do we call it plane? Well, there is no x dependence in the amplitude. Right, there's an amplitude and there is a phase. The amplitude is constant, meaning the wave is propagating in x, there is no decay of the amplitude. And then there is no y and z dependence, which really means it's flat, plane. So it's very suggestive, it's a plane wave. Only the phase changes. So it's an infinite plane, constant amplitude, only the phase is changing with x, right? At a rate that is exactly k naught, right? So I get every 2 pi over k naught meters, I get 2 pi of phase. And k naught is the material property. If the refractive index is different, k naught changes, right? So this is, I'm sure all of you have heard of plane waves. And the good thing is that now, if my source is not a flat screen, which is very kind of impossible to generate in the lab to begin with, but if you have an arbitrary problem with an arbitrary source, you can decompose your generic problem into a summation of plane waves. So we're going to see how that works in microscopy, for example. Okay, so basically what we did here, we solved a very simple problem of an infinite planar source that emits in x and minus x. And using the Fourier transform properties, we were able to solve this very quickly, and we obtained that along the positive axis you get the planar solution, which means the amplitude is constant, only the phase changes, and only in x. Hence, it's a 1D solution. Any questions so far? So the reason I'm showing you this, even though it may look like very basic and boring, is that most of the books of optics, at least those that I grew up with, usually say it can be shown that a plane wave is a solution to this equation. So you go the other way around. You know the solution, you plug it in, and you show that it goes to 0, therefore it's a solution. I'm showing you how to actually solve the equation without assuming anything. So I think that is useful. What happens if I choose the wrong coordinate system? So this is my source, right? So this emits light like this. I'm on that or whatever. But now let's say for some reason I choose my coordinate system this way. Well, the solution can be simply, you simply rotate your axis, for example. But the way to fix this in the solution is to just write k dotted into r. So it's a dot product between the wave vector and r, which takes into account the fact that I got the picture. All right. So if you plot the, again, if you plot the amplitude versus x, it's a constant. That happens to be 1 over k naught. If you plot the phase of the solution is linear, right? So it's e to the I k naught x. So it's linear in x, and the slope is k naught. So if you have a plane wave going along x, you get k naught times x. But now if you have a plane wave that propagates at a strange angle with x, that's when you take your k vector, which is this, and you project it. Your k is not parallel to the x-axis, you project it onto r. And that is what we have here. This tells you that basically the phase only changes perpendicular to the wavefront. If you look within the plane, there is no phase change. That's what this one is. So when k is perpendicular to r, there is no phase change. Any questions about plane waves? This is a very basic concept, but it's very useful in imaging because pretty much any wave can be decomposed into a summation of plane waves with different amplitudes and different phases. So in a microscope, when you focus the light down, you get all these plane waves along different directions and you overlay them to the sample. Any questions? Nothing? Still jet lag? Okay, let's move on to another basic thing. What happens if now I have a 3D problem? Meaning my source is now a point source. It's a quantum dot or a molecule by itself in the universe that emits light. What's the solution? How is the wave coming out of that? How does that look like? I think all of you know what the solution is, so what is it called? Spherical wave. But I want you to know how to solve the equation as if you don't know. This is the Helmholtz equation with the source now as a delta function in 3D. It turns out the Fourier transform in 3D of this thing is still 1. The Fourier transform of the Laplacian I showed you earlier gives you minus k squared, where now k is scalar, is the length of the k vector, so it's k squared. K naught, so it basically looks almost like in the one-dimensional case, except for one little difference. Instead of kx, I have k, which is the magnitude of the vector k. And that turns out makes all the difference. How do I solve this? Well, I'm doing the same thing. I can break this into two, so the positive k and the negative k. What does that mean? If I have this quantum dot emitting light, it's as if I'm having a spherical wave coming out of it, and then I'm spherical wave that comes in. You overlay the two, you get something like a real function. But again, we're going to keep it in the complex form. So, the final solution, overlaying these two, is basically this. So you still get the cosine of k naught r. So notice, last time we got x, so that was a one-dimensional problem. Now we got r, except that it's r scalar, so it doesn't depend on the direction, which coordinate direction I'm looking at, because it's spherically symmetric, right? I'm starting with a point in an infinite space. So obviously you expect a spherically symmetric solution. And another interesting thing is that now I have 1 over r in the amplitude. What does that tell us? What do you think? The amplitude goes down. Why? Otherwise you couldn't conserve energy, right? So you start with light from a very small dot. Now that wave grows, so your sphere goes larger and larger. Obviously, to keep the power conservation, the amplitude has to go down. In amplitude is 1 over r. In power, it will be 1 over r squared. So it makes perfect sense. Again, this is a spherical wave. You can keep it in the real form like this, or like most people, you keep it in the complex form. And this is the classical kind of equation for a spherical wave, e to the I k naught r over r. Again, k naught, that material constant, the propagation constant, some people call it, is in there. So it tells you no matter what direction I'm looking at, from the source going outward, I'm making this many radians per unit space. And that number is given by k naught. Refractive index is in there, omega is in there, and c is in there. Okay? So, now if you look at the amplitude of g, so my wave, I call it g for Green's function, or in engineering terms, impulse response, is the solution to a delta function. So g of r goes down as 1 over r. Keep in mind the intensity would be 1 over r squared. And then argument of g, meaning the phase, is linear with k naught. Again, the slope of that phase is k naught. Now, for those of you familiar with linear systems, once we know the impulse response or the Green's function, and I know my system is linear, can we solve an arbitrary problem? So instead of a delta function, one quantum dot at the origin, I have now a distribution of them, a bunch of sources. Can we write directly the solution to that, once I know the solution to a point? The answer is yes. What is that solution? It's simply the convolution between the input, the source, and the spherical wave, which is my impulse response, my Green's function. Okay? So you see that we're able to write, if we know that the system is linear, we use very basic linear system properties, and we can write directly the solution to any arbitrary source as a convolution between the input, that source, and the spherical wave. So this is a convolution integral, right? So it's f of r prime times g of r minus r prime, integral of r prime. That's the definition of a convolution. What do you notice? The integral gets ugly quickly. Right? It's hard to solve this thing. Like this. That's a magnitude of r minus r prime, that's at the bottom. So normally what do? We start to approximate things, right? And basically, when you can approximate the integral, what I prefer to do is to approximate my Green's function. So the Fresnel approximation is very, very useful and common, and makes that integral more tractable. So first of all, let me tell you something. Propagating fields from a source, it's kind of looking at a wrinkled shirt. This is how I show my students. So you start with a very wrinkled shirt, meaning the field has very, very high structure. If you like, the spatial frequencies are very high. So you have a lot of structure, but as it propagates, it's kind of like a balloon that all those wrinkles are smoothed out. So the Fresnel approximation takes into account that smoothing, and it says, well, if I observe at a certain distance from the source, I will kind of take into account this smoothness. So I make this approximation that the fields are actually, I'm looking at the large distance from the source, and you can actually do the real thing and you calculate the near field solution close to the source, but it's a much harder problem. Okay, so if you want this in this diagram, near field works everywhere. Then you have the Fresnel approximation that works from some distance outward. And finally, you have the Fraunhofer approximation that works at even larger distances, but the solution is even nicer. You know, the stronger the approximation, the nicer the solution is. Hopefully, otherwise you shouldn't make that approximation. Right? So, keep in mind, it's like a balloon that is kind of all crumbled up. Once it propagates, the larger the distance, the smoother the balloon gets, right? That's what we're trying to do with the Fresnel approximation. So basically, looking at the spherical wave, what can we do to it? First of all, after a certain distance, after a pretty large distance, I can say that the amplitude 1 over r actually stays constant. Stays constant in x and y, meaning r and z are kind of the same. So you see what that's equivalent to? It's saying that, okay, I'm looking at this coordinate r, and z is this much from here to here. I'm saying that r and z are kind of the same. Right? So I'm ignoring, if you want, I'm ignoring this little segment right here. Right? The difference between r and z. And that's okay, right? You see how that's okay. If you're far away from the source, that's a good approximation. Okay? So that was easy. We simply ignore the x and y component of r. The trouble is that if you're trying to do the same thing in the exponent, in the face, you run into trouble. If you just replace r with z in here, you get e to the ik not z. And what is that? That's a plane wave, the plane wave that we just saw a minute ago, right? So that really is a very crude, terrible approximation. That says my wavefront is flat. So there is no structure in x and y. So if you want to calculate any imaging or anything like that, there is lost, right? So that's really probably from very, very far away where you are trying to keep track of the phase along z, but nothing else, right? So that's too crude. So what do we do in terms of phase? Well, we have to be a little bit more accurate. So we're trying to expand e to the ik not r, where these are scalars. So r is square root of x squared plus y squared plus z squared. I'm saying x and y, meaning the observation plane over there is much smaller than the distance from here to there, right? So that's fine. So then I can factor z out, and I have z square root of 1 plus blah 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 over z squared. And I'm applying a Taylor series. Square root of 1 plus x is about 1 plus x over 2. That's what this one is. Are you with me? Yeah? So this is just Taylor, the Taylor expansion from here to here. So when I put this in the exponent, what do I get? So remember, we changed the r into z. So I have e to the ik not z over z. So this is this first term. And then the interesting term is this. So I told you if we were to do the crude approximation, we'll be left with only that. There will be no x and y. That would be terrible. You could never calculate an image or anything like that. But we kept that. So we have e to the ik not x squared plus y squared over 2z. What is that? This function. What is that called? What's a function that looks like x squared? From 6th grade.
Quadratic.
What? Okay, it's a parabola. Fine, but then it's okay too. It's a parabola, right? Like as in parabolic antennas. Get it? Right? So it's a parabola. It doesn't matter what it's called. It's basically this whole thing looks like a Gaussian now, right? E to the x squared is a Gaussian. So essentially, we approximated a spherical wave with a parabola, meaning this is a sphere. We approximated with a function that is more like that. And that happens around small n. And that's fine for large distances. You see, that's all we did. But the beautiful thing is that now we ended up with the Gaussian, and we know how to take Fourier transforms of Gaussians, right? What's the Fourier transform of Gaussian?
Gaussian.
Gaussian, good. What else do we notice? I like to pay attention at simple equations, like look in detail. You learn a lot of things. So you have a parabola. What's the width of that parabola? So you can have a parabola that's very skinny, like you get the U that's very tight, right? Like a aerial narrow U, and then you can get a regular aerial U. What's the difference between the two? This Z at the bottom controls the width of that. Or if you want, if this is a Gaussian function, if you think of it as a Gaussian function, the width of that Gaussian has Z in the bottom. Meaning, the more you propagate the field, the fatter the Gaussian. Right? So you have a Gaussian of a certain width, it has Z at the bottom. Okay, so 2 alpha squared. Alpha is the standard deviation of the Gaussian, right? It's the width of the Gaussian. In our case, alpha is basically square root of Z, right? Because my Z appears as linear and not square. So what does it mean? As I propagate in Z, my Gaussian, or in other words, the distribution of the field in X and Y, becomes a fatter and fatter Gaussian, and the width of which increases at the rate of square root of Z. Which means a very simple thing. If I propagate this beam, the farther I go, if I go a mile away, that spot is going to grow larger. The width of that spot is going to grow with square root of Z. Okay? Good. So now we go back to doing this integral. This kind of integral. So now my input is arbitrary. What is the field from that arbitrary source? In particular, a very common problem is, imagine I have a planar source. So I have a source that looks like this. Or this could be an aperture that actually is illuminated by a plane wave. This is essentially any diffraction problem you can think of. See the random aperture at the plane. Well, it could be a primary source. It could be our, I don't know, fluorescent source over a certain domain. It turns out that at this point, after 15 minutes in our lecture, actually a lot more than 15 minutes, we're behind. We are able to write the final solution quickly. This is the Gaussian, this is the Fresnel approximation up there. This is my input. This tells you the field distribution at this plane. U1 gives you the field distribution at a certain distance Z from this, according to the Fresnel approximation. And what do we notice? You get the Z's in front, no X and Y dependence. And then the X and Y dependence is simply a convolution between this and that Gaussian. And this is my sign for convolution because it has a V in it, it's a V circle. So is the input U convolved with the Fresnel kernel, with the Gaussian kernel. So basically at this point we're able to solve any diffraction problem. You tell me if U, the input is a square, if U is a sinusoidal grating, you just write it down. If U is a star, or I don't, do you remember those pointer masks where you illuminate with a bunny here, right? Or a smiley face? You know those? Okay. How do you think those are made? Well, you put the Fourier transform of the bunny or smiley face right here, and by the time it propagates over there, by the time you do this convolution, it turns into a smiley face. Okay? What's the relevance of this to microscopy, do you think? Anything? So I have a field at a certain plane. I am able to predict the field at a different plane. Z distance away. Is that relevant to microscopy? Convolution. When does this apply? Using Hazer resolution. If you go backwards using Hazer resolution, is that what you mean? So you see, this convolution is a blurring operation. You see, you are basically taking the field and actually convolving with a Gaussian function. It means that you take points that are infinitely small like this, and you convolve it with the Gaussian of a certain width that looks like this, and the result is that Gaussian shape. So if your image is made of many different points, what you're going to end, and let's say very fine structure, what you are going to end up through convolution is a much smoother function. which is to be expected. If I start with a field here, with the crumpled field that I told you, the balloon or the shirt, as it propagates, it's smoothed out. In microscopy, this is the solution of an image that is out of focus. So I take my perfect image in focus U, but now for some reason, I put it out of focus. So what do you notice? You lose your details, right? That's what happens in a microscope. When you put your image out of focus, or that camera, when you put that camera out of focus, you blur the details. And the reason is because of this convolution operation with that Fresnel kernel. Very simple. Now what Mohammed was saying is that you can go backwards, so I have a smooth function. If I know this kernel of convolution, I can numerically take it out. And I can sharpen the image, so I go backwards from here to here. That is doable, especially when your signal to noise is very high, because any noise you add to this kind of makes things harder. But the convolutions work. So you can actually recover details that are otherwise blurred by a certain convolution operation. Any questions about this? Is it crystal clear? Or there's another explanation why there are no questions? Yeah.
You can come back when their material has an equal to 1, or it is we have something for the refractive index and can come back. Can we reconstruct?
Good question. So if the refractive index is constant or homogeneous, there's no problem. K naught has an N in it, but you don't care. Well, I think what's
Could you repeat the question?
yeah. So the question is, can we do this deconvolution when I have a refractive index that is non-1, meaning I'm not in vacuum, right? So if you are in glass, the equation is the same except that your K naught is bigger. It's N times omega over C. But I think what you mean is what happens in cells when you image things. Okay, so that's a harder problem. That is, we're going to talk about it in a second. But imagine now that your N is different from point to point. That's when things are getting, depending on your point of view, uglier or interesting. So we're going to talk about that. It turns out that we know how to solve that problem when the refractive index change is not that strong. Meaning you have an average refractive index and then fluctuations of their refractive index. Like in the cell is a good example. Their average refractive index is kind of a little bit higher than water, but not much higher. And then you have fluctuations. Let's say you have 1.35 plus or minus 0.001. So that's a perfect example where a live cell unstained is weakly scattering. And it turns out we can solve that. We can linearize the problem under the Born approximation, and that's what we're going to talk in a second. But we have to be a little bit more careful. So it's not as simple as that. The problem becomes three-dimensional. It's not a plane. The cell is not planar. It's actually a three-dimensional volume. The refractive index depends on all three coordinates. Very good question. But are we clear on the diffraction problem? Yes?
Well, I guess in terms of application too, so when you have something where you have so many data points and this in and out,
Yeah.
how do you prevent data loss or like creation of unreal information on your
When you deconvolve.
Yeah.
Yep. That's actually an important problem. That's the reason, actually, in my lab, we don't let the convolution run forever. So you can actually run the convolution in loops. And you end up with resolutions that are incredible. Like you start to see 10 nanometer dots in your images. The question is, are those real, right? That's your question. And sometimes, most of the time, it's very hard to tell. So we usually stop at improving resolution at the factor of 2 or 3. That's kind of okay. The rule of thumb is the signal to noise, you can improve it by kind of, the resolution improvement is about square root of your signal to noise. So it gets exponentially bad. As you add noise to your system, the deconvolution gets exponentially bad. Okay? So there are people who make careers on deconvolutions. Actually, I'm not one of them. We were lucky to work with the Beckman fellow here, with a postdoc who actually now works for Google. So he had the deconvolutions already running for other applications, and we put our phase images in, and it was a beautiful match. But we always ask this question: at what what point do you bet your children's life that that dot is real, right? So you have to look at the signal to noise end. And the fact that it gets exponentially bad, that's important. I notice some people don't have those emotions, and they claim 50 nanometers with far field. I've seen that, but you have to always question. Okay. Have I been speaking for a whole hour already? Okay, let's do this thing, the Fourier. So let's do the Fraunhofer approximation, and then we take a break. It'll be a short break. So there is, if you go even farther from the source, in other words, if you look at angles that are even smaller, you can do an extra approximation. So looking at this convolution kernel, remember you had x minus x prime squared plus y minus y prime. Basically, you can ignore the quadratic term, x squared and u squared. You just take them out, and you end up with just the linear terms, right? So we expand this x squared minus 2x u plus y u squared, and we neglect the quadratic term. In that case, you end up with these linear terms. This approximation is called the Fraunhofer approximation. But the beautiful thing is that your integral now becomes that. So this is the integral we had before, except that we, instead of x minus u everything squared, we ended up with just a linear term. And now you should notice that this integral looks like this. It's like my input, u and v, e to the minus something times u plus something else times v. So it is a Fourier transform, provided your spatial frequency is defined by this. Kx is 2 pi x over lambda z, ky is 2 pi y over lambda z. So from the ugly integral, the convolution with the squares in it, with the Gaussian, if you go much farther to the source at the point where the u squared and x squared are negligible, so meaning my source is small, the domain of the source, and the domain of my observation is also narrow compared to this distance. In that case, you end up with a beautiful result, and that is that in the far field, you get the Fourier transform of the field right here. So that's what I mentioned with the bunny faces, with the smiley faces. If you put the Fourier transform of a smiley face here, and you let it propagate in the Fraunhofer regime, you get the actual smiley face there. Okay? Now, the spatial frequencies have x, z, and wavelength, but they have x and z in them. What does that mean? Well, it means that kx is proportional to x, meaning the larger the distance from the origin, the higher the frequency. What does that mean? It means that if my field here, my impulse field here, has high frequencies in it, in order to observe those, you need to increase your angles. Because x over z, right, x over z is actually exactly this angle theta. And is that relevant to microscopy? Yes. It means that if I have fine structures in my object right here, I better increase the angles of collection. Okay, that's where the money goes when you buy expensive objectives, right? High numerical aperture. So numerical aperture in microscopy terms is simply the sign of that angle, sign of theta. So you can buy objectives now, you can pay $12,000, which is more expensive than some of your cars, I assume, that collect most of these angles. So if this is your sample here, you can collect like almost the whole 2 pi semi-space. So you see, we learn from these simple equations, we learn something very basic, how microscopes work, right? And the relationship between the frequencies of the object that you're trying to measure and actually the field that you're measuring and fact that you need to collect large angle. And notice the wavelength plays a role also. How does the wavelength affect things? So Kx is proportional to 1 over lambda. What does that tell you? The shorter the wavelength, the higher the frequency. What does that mean?
Resolve more.
You resolve more with shorter wavelengths. Right? So in microscopy, it means that you're better off in blue than in red, or even better in ultraviolet than in visible, even better in X-rays than in any other one. You can go all the way to gamma rays. How about electron microscopes? Same idea. The de Broglie wavelength associated with electrons is very, very tiny, much shorter than X-rays. They're actually 10 to minus 3, for example, nanometers. It's a funny fact that you should be able to see single atoms with no problem with the electron microscope. But the basic problem is aberrations, which sounds kind of boring, right? But the reason we don't see atoms right away with an electron microscope is not because of this. The physics will allow it. It's just because of spherical aberrations. So that's kind of sad. So this is the reason why we like short wavelengths. But now, why is it that we don't have all of us have X-ray microscopes in the lab and get it over with this visible stuff? Well, they tend to kill stuff. That's one way. Optics is a luxury that we kind of have it for free in the visible regime. Try to build optics for X-rays. It's a whole different problem. You cannot bend X-rays with transmissive optics. It has to all be reflective at very kind of shallow angles. So there are practical issues with X-rays also. How about UV? Okay, let's be a little bit less ambitious. How about UV? Well, we use UV mostly for in microscopy. What do we do with UV? Okay, that's a kind of, I like to think it's a collateral thing, but we mainly use it to excite fluorescence, right? So we excite in UV, we get lower energy photons out in the visible. But it's true, UV kills things. UV, that's the reason we cover ourselves when we go to the beach with various creams. It may affect your DNA, meaning the energy of the photons is so high in the UV that it can create electronic transitions. So we're very lucky that we work in visible, but at the same time we have to be cool with the fact that our resolution is kind of not great. And with visible, we have resolutions of the order of the wavelength of that light, which is half a micron roughly speaking. And the main challenge is that you would like to, which is 5-way imaging cells, but the main problem is that we're far away from the molecular sense, right? So ideally, we want to go from 1 micron to 1 nanometer, right? Because if we manage to do that, then we'll be able to image molecules, at the same time zoom out, image the whole cell, and hopefully one day understand how all these molecules are working together. Right now, there is this gap. There's a black domain from the molecular scale to the cellular scale. And that's why all this discussion about super resolution technique is so important. That's why the efforts, at least in the past decade or so, were so intense on super resolution. It was proven that actually we can break the diffraction limit, so this discussion can actually be exempted in some cases when there is no linear interaction rather than linear between the light and the sample. So that's why it's so crucial, because if you have an imaging system that shows you molecules and then shows you the whole cell, then it's going to be beautiful. Because hopefully we'll understand how all the molecules work together. Right now, I think part of the problem with the whole understanding of how cells work is because we have this gap. So bridging molecular biology to cellular biology is a major thing. Okay, so quick example and then we take a break. If you have a very simple diffraction problem, I have a sinusoidal grating. So by the way, if you think gratings are boring, think again. The inventor of phase contrast microscopy, who got the Nobel Prize for it, Zernike was playing with gratings when he invented this thing. So, understand simple problems very well. That would be my advice here. So if I have a sinusoidal grating whose transmission is 1 plus cosine of something, so this is a one-dimensional problem. I have a sinusoidal this way. I'm sending light, I'm trying to figure out the field diffracted by that. All I need to do is to take the Fourier transform of this whole thing. I put it in there. What's the Fourier transform of a cosine? Don't look. 2 delta functions. Why? Because the cosine is e to the I something plus e to the minus I something. The Fourier transform of each of the e's is a delta function. So the cosine is 2 delta functions, 1 to the plus, 1 to the minus. And not surprisingly, that's what you see coming out of a diffraction gradient. The Fourier transform of the 1 of the DC gives you a delta function in the origin. So this is the 0 order. Let me color code this. So the dash 1 is the 0 order. 0 frequency means 0 angles. That's your 0 order. The first delta function gives you plus k1. This is the first order of diffraction. And this one minus k1 gives you the minus 1 order of diffraction. So if you didn't know the Fraunhofer approximation, the Fourier transform, it will take you a little bit of calculation to do this. So I remember in high school you will have to do the geometric optics thing, look at the path difference between the two orders, right? And then make that integers of 2 pi. That works. But how much more elegant is this, right? I know 1 plus cosine Fourier transform gives me 3 deltas. 2 symmetric ones plus the one in the middle. That's what you see out of a diffraction gradient. Why is this relevant to microscopy, for example? Because you can write any object as a superposition of many different gradients. Any object, including yourself. So basically that's the best way to understand how a microscope works, by thinking of these gratings and making up yourself out of gratings. That's what Abed did. Okay, this tells me that I really talked for 1 hour. There's no misunderstanding. Okay, let's take a break, maybe 10 minutes. Would that be okay? Good, thanks. I learned that if you propagate the field far away from the source or from an object, diffractive object, at the end of the day you get the Fourier transform of that field. Right? So it turns out that there's another way to take the Fourier transform of the field, and that is a much more practical way, and that is using lenses. And here's a quick proof of that. So let's imagine I have a transmission function of the lens that looks e to the I phi of x, meaning if I have a plane wave like this incident on a lens, this is a thick lens, and I start with a plane wave in front of the lens, the question is what will be the wave front right after the lens? Very simple problem, right? And if you do all these calculations, so you take into account the thickness of the lens, and then you make that approximation that the angles are small, and I'm not going to go through all the details, but if you do all that, you end up with the fact that the phase in that transmission function looks like this. So you have a DC that is kind of unimportant, it's a constant phase shift. But then the interesting part is this. So you have K naught, our old friend, and then you have an R squared, this is X squared plus Y squared, so this is from the optical axis, distance R. And then you have this whole thing. What is this? This is the radius of one surface, radius of the other surface. This is n minus 1, n is the refractive index of the lens. What is this whole thing?
Focusing power.
Focusing power. The inverse of this whole thing is the inverse of the focal distance of that lens. So, long story short, if you write a transmission function of a lens, so this is again, I have a plane wave incident on a lens, what do I get right on the other side? What you get is e to the I is something that is constant and unimportant, and then you get this thing, which is simply e to the minus k naught x squared plus y squared over 2f. Okay, what does this remind you of? Gaussian. It's the same kernel as as the Fresnel in the Fresnel approximation, except that what is different? What's the width of the Gaussian now? It's F. What did it used to be? What did we have there before? Z, right? So it means a very simple thing, that I get kind of the same result as I'm propagating with the Fresnel approximation, except that I don't need a large distance, Z, right, for that to happen. I can actually use something more confined, like a focal distance, which means that we can do image processing and all these Fourier transformations we're going to find out in a very compact form. You don't need that miles of propagation for the tropical approximation to work. So it's a very practical thing. So basically, this is the Fresnel approximation. Let's say I have a point source that diverges, right? This is equivalent if I have now the same field through a positive lens, through a convergent lens, that is going to be convergent. But the Fresnel propagation is actually identical to propagating through negative lens, divergent lens. So if I have, let's say plane wave incident, this is diverging, it's as if it's originating at this virtual focal point. So you see why they look the same, right? Except that now I have Z in the Fresnel propagation and I have F in the lens. But everything else is the same. So in fact, this is the more relevant thing to your microscope putting things out of focus. It's the objective focal distance that actually goes in there. It's not only the Z itself. Okay. Then what do we do with this? Well, ideally what we'd like to do is to take some field at a certain distance from the lens, propagate it to the lens with a Fresnel approximation, to the lens, propagate it to the lens, then propagate it through the lens using this transmission function we just found, and then propagate it to an arbitrary distance d2. Why would we like to do this? Because if I know how to propagate through one lens, then I add a second lens and I make a microscope, I make a telescope, I make anything I want. Well, if you want to do that calculation, basically you have to take from the original plane to the lens, that's a Fresnel propagation, that's a convolution that looks like this. At the lens, you take that field U2, this one, take the result, and you multiply it with the transmission function, which is exactly this one that we found earlier. And then you take that field at the back of the lens and you propagate it to D2, and that's another ugly convolution. So try to do this for 5 minutes and see how ugly this thing gets, right? But then something magical happens. If I put my object, where's the figure? Right here. If I put my object right in the focal plane, in other words, I make D1 equal to F, and then I make D2 equal to F, meaning I put my input plane right in the focal plane and my observation plane right at the back focal plane of the lens. A bunch of terms cancel out, and my final result is just beautiful, like this. Except for a constant that we don't care about, you get that the field at the back focal plane is the input field, let's say that one, Fourier transform. It's exactly the equation we got for the Fraunhofer approximation, except that now the K's used to have x over z in them, now they have x over f. But the math is the same. So this adds tremendous practicality to the Fourier transform, because before we needed a large distance. Sometimes for an object this big, probably your lab has to be a mile long to get Fraunhofer approximation. Now with this, that doesn't have to happen. You can actually make this work over very kind of finite on your optical cable. So this is unleashing a lot of possibilities for us. Now you notice how f is very important and x is very important. X over f gives you some kind of a numerical aperture, right? It's the largest angle that you capture from your sample. So, for example, in the sinusoidal grating example, let's do it now with a lens. It's a lot more compact. of a diffraction problem, right? So I put the diffraction grating right here. This could be your objective of the microscope, for example. What you get on the other side, you still get the Fourier transform, you get your 0 order -1 plus, it should be plus 1, right? Get the same thing, except that your F shows in there. So if you understand the grating, you understand now that if that lens goes into your microscope, into the objective of your microscope, the smallest period of the grating will give you the resolution. And that's only related to the angle that the lens can capture. Period. That's your numerical aperture of the objective. That's where you pay the money to make a good object. Any questions? Yes.
So you mentioned for proper approximation to bulb, you have to go far away.
Yeah.
For Fresnel, how far is would you not?
I didn't give you any hard numbers and I kind of avoid to do that. So if you look in the terms that you neglect, look at what that means. So for example, we neglected x squared of lambda z, something like that, right? So now you need to particularize what you're looking at. So x means how big is your object, right? U means how big is your observation plane, or the other way around, I forgot which is which. So then, okay, I'm looking at an object that's 1 millimeter. What's the distance z for which this becomes 1%? So you come up with the length. Okay. So it's not a fixed number, 1 mile. It depends on your object, it depends on your angle.
This is 1% in the exponential, or that
Yes.
propagates more.
Yeah, so pick your negligible point. 1% is a safe one. So it's not a clear cut, right? It's not a jump, it's all a gray. You can put up with more errors, then. Oh, so let me ask you this, intuitively, what happens if you are not quite in the Fraunhofer Fourier regime? What happens to a Fourier transform? You don't get an accurate Fourier transform. What do you get?
Is there a phase term or something like that left?
Blurred. Who said blurred? Good. Yeah, so imagine my perfect, this is in the Fourier transform. This is a safe Fourier transform, Fraunhofer regime. But for some reason my lab is short, so I'm observing here. Okay? So this is not perfect. How is it different? Well, it's different by propagating this from there to here.